This video demonstrates the use of MATLAB with state space model analysis. Previous videos then have demonstrated numerous mechanisms for creating state space models to represent systems. And here's a typical state space model. X dot equals AX plus BU, Y equals CX, where X is the states and A, B and C are the model parameters. Now you'll have noticed a problem immediately here, that state space models involve the use of matrices, and matrix handling is not in general a paper and pen exercise, and so I would recommend that people use computer tools such as MATLAB wherever some number crunching is involved. Now the code in support of this particular video is in statespace9.m, which you can get on the website if you want it. First examples then. Now this file ss.m is probably the most important file you'll find on MATLAB, and it's a specific format that MATLAB has created for storing state space systems. Once you have put your state space parameters in through this model, then you can deploy a number of other MATLAB functions for analysis and design, and you'll be familiar with some of these, things like step.m, impulse.m, pzmap.m, feedback.m, bode.m, nyquist.m, and so on. Now there are many more, and you might want to look at the chapter on use of MATLAB for other illustrations. Some examples then. What I've put in the middle here is the code that you would actually put into MATLAB. So if you write the code precisely as shown here, then it will work. So I'll do this one first. So I've put the A, B, C in, and what I've shown in this window is what comes out with the last command. And you can see that MATLAB tells you that G is a continuous time state space system, and it's told you what the A matrix is, the B matrix, the C matrix, and the D matrix. So it now understands G as an object which stores a state space system with parameters A, B, C, and D. Now that was a 2x2. If you were to do the 3x3, which is this set of code over here, then you can see the answer over here. So that's illustrated the command ss.m. Now, using other functions in MATLAB, again you'll see the first block of code here defines the state space matrices A, B, C, D, and then uses the command ss to generate a state space object G. And once I've got that state space object, I can use it in functions like step, which is illustrated here, pzmap, which is illustrated here, or indeed feedback, which is illustrated here. You'll see that it's given you an amended state space model to show you what would happen if you connected this with unity negative feedback. What about some of the transformations then that we've been doing in the videos so far, like transfer function to state space? So here's a state space model, and what we're saying is there's an equivalent transfer function model, and you might want to go from one to the other. Here's an example then. You'll see I've defined the transfer function parameters n and d, that's for numerator over denominator, and then I've used this command here, tf to ss. So tf stands for transfer function, ss for state space. So what this function does is it goes from transfer function to an equivalent state space model, and you'll see here it's given you an equivalent A, B, C and D. It's not given you an equivalent state space object. What it's given you is the A, B, C and D matrices, or one variant of those matrices, given they're not unique. Second example, over here you'll see slightly higher order transfer function, so n's got 3 terms, d's got 4 terms, and again here is the corresponding A, B, C and D. You'll notice that it's putting it in control canonical form because you'll see all the parameters there on the top row. How about state space to transfer function? Now a bit of a warning here that this is done for CISO only, as you need to be a lot more careful for multivariable processes, and that detail is beyond the remit of this series. So again, that's the equivalence we're looking at, and you'll notice what we've done here is we've defined our A, B, C, D matrices, and then we've used this command ss2tf. In other words, go from state space to transfer function. Here are the state space parameters, and here are the transfer function parameters in N and D. So you'll notice N here, D here for that top example, and for the bottom example, which is slightly higher order, there is the N and the D. What about similarity transforms? And again, because these involve matrices, they'd be quite tedious to do by hand. We all know that matrix multiplication is not simple. So we'll demonstrate that you can do this easily on MATLAB. First then, we've entered our A, B, C and D up the top, so that's defined our original matrix, and then I've defined an arbitrary T. T can be anything you like, and I'm here making it arbitrary as long as it's full rank, and then I've defined T inverse as Ti, and then what I'm going to do, if I go back here, you'll see that the transformations we're talking about are these ones here. A hat equals Ta T inverse, B hat is TB, C hat equals C T inverse. So if you look at these commands, there's A hat, and there's B hat and C hat. So all I've done is define the transformed matrices. Now what do I do next? I've formed a state space object with the original matrices A, B, C, D, and a state space object with the transformed matrices A hat, B hat, C hat. Because what I want to do is compare G and G hat. The conjecture is that G and G hat represent the same system, so they should be identical. So I've calculated a step response with G and a step response with G hat, and then I've overlaid the two responses on this figure up here. And what do you notice? They're both identical as expected. The next thing I've done is I've compared the eigenvalues of A, there they are, and the eigenvalues of A hat, there they are, and again you will see they are the same as expected. What about diagonal canonical forms? So the diagonal canonical form came from using the eigenvectors as your transformation matrix. So that's what we did. We basically wrote A hat as W inverse AW, B hat as W inverse B, C hat as CW. So here I'm going to do it. There's my A matrix. First I find the eigenvectors and the eigenvalues. There they are. And then I define A hat as inverse W times A times W. And I compare it with lambda. And here's the results. You'll see that A hat, as expected, is in diagonal form, and what's it got on the diagonal? It's got the eigenvalues. So it's done exactly what I expected. Okay, using MATLAB to find transformations which give canonical forms. So MATLAB does have a command, canon.m, which will give you some canonical forms. Not all, but some. So here's a first example. What you'll see, if you look at the top here, is I've entered my A, B, C and D. I've created my transfer function, my state space object with this ss command, and then I've used canon G, and then I've used the command modal. Now modal form is essentially saying put it into diagonal canonical form and find the T, the transformation matrices that will do that for me. So if you look, you'll see the corresponding A matrix is diagonal as expected, with obviously the eigenvalues on the diagonal. Here's the corresponding B, here's the corresponding C, and over here, here's the corresponding transformation matrix. I could, with this canon, use a different command, which is companion. And if I put it in companion form, you'll see what it's done is it's put the key parameters here on the last column, and that's an observable canonical form. So in summary, we've demonstrated the use of MATLAB for definition and analysis of state space systems, easy to plot behaviors, to form closed loop systems, to find poles, do state transformations, and so on. Now, what we should do quickly before we finish is just remind you that the code is provided for you in this state space file. So if you go to state space 9, you'll see all the codes there. You can select the different bits you want, and you can run them. So if you want to see and run them, just download this file and it will repeat what we did in this particular video.